Beyond Earth's atmosphere, air disappears, pressure collapses, and temperatures swing violently.
In microgravity, even simple movement becomes a challenge, and without protection, organs.
To survive outside Earth's protection, engineers must create a wearable system that replaces atmosphere.
Maintaining internal pressure is critical because even small leaks can cause swelling, impaired movement, and rapid loss of consciousness. Each layer serves a different role, from holding pressure to blocking radiation, and together they form a barrier only a few millimeters thick. A fraction of a millimeter matters here, because every panel must align perfectly once the suit begins to take shape.
Every seam becomes part of the structure, carrying pressure loads while allowing joints to bend without tearing. Clear vision is engineered layer by layer, protecting eyes from glare, debris, and sudden temperature changes.
Breathing, cooling, and carbon dioxide removal are routed through hidden channels, turning fabric and tubing into a fully functioning life support system.
Mobility is carefully engineered, because stiffness or resistance here can turn simple tasks into exhausting physical strain.
Hands must remain sensitive and strong, allowing complex tools to be operated while sealed inside a pressurized environment.
Heat has nowhere to escape in space, so internal cooling systems quietly manage body temperature every second.
And communication and monitoring systems are woven inside the suit, ensuring constant contact and vital data flow during every operation. This is the first moment the suit comes alive, revealing whether every seal and layer can withstand controlled internal pressure.
Even the smallest leak can become dangerous, so every seam is tested until the suit proves it can hold steady under stress.
Once pressurized, the suit must still move naturally, because restricted motion can drain energy and limit precision during critical tasks. Inside the vacuum chamber, the suit faces the same emptiness it was built for, proving whether protection holds when air disappears completely. Temperatures can swing violently in orbit, so the suit is pushed through extremes to ensure stability when conditions change without warning. No two bodies are identical, so each suit is carefully adjusted to balance comfort, mobility, and long-duration wearability. Before real missions, the suit is worn through repeated simulations, revealing how design choices affect performance during extended operations. Hours of continuous wear reveal hidden pressure points and fatigue, helping engineers refine comfort for missions that last far longer than expected. Only after passing every technical and human test is the suit approved, marking the final step before it can support a real mission. Once approved, the suit is stored under strict conditions, remaining mission-ready until the moment it is finally needed.
In the final hours before launch, every component is checked again, because once sealed, there is no room left for correction. Putting the suit on is a controlled process, where each seal and connection must lock perfectly before pressure is introduced.
Breathing pure oxygen before departure reduces decompression risk, allowing the body to adapt safely to changing pressure levels.
With every system confirmed, attention shifts from preparation to execution, marking the quiet transition from testing to real operation.
Every step toward the vehicle carries months of engineering, turning careful preparation into forward momentum. Once seated, external support lines take over, keeping airflow and cooling steady until the spacecraft assumes full control.
At this point, the suit becomes a silent partner, continuously regulating life, while teams track every signal in real time.
As forces increase during ascent, the suit quietly maintains pressure and temperature, keeping the body stable through rapid acceleration.
Once in orbit, control shifts to onboard systems, and the suit continues its role, managing airflow and temperature without interruption. Before stepping outside, the suit becomes the only barrier between life and vacuum, making every checklist item essential.
As air drains away, the suit fully takes over, maintaining pressure and oxygen while the chamber falls silent.
Outside the spacecraft, the suit becomes a complete personal environment, supporting life where nothing else exists.
Every movement now relies on joint design and grip strength, turning engineering decisions into real-world performance.
Cooling, oxygen, and carbon dioxide removal work continuously, keeping the body stable while effort and exposure increase.
Even small pushes transfer force through the suit, testing its structure while delicate work continues in zero gravity.
Every heartbeat and temperature change is tracked from Earth, adding another layer of protection far beyond the suit itself.
After hours outside, the journey turns inward, bringing both crew and suit back toward controlled pressure.
As air returns, the suit gradually hands control back to the cabin, completing its role in keeping life protected.
After re-entry, systems are checked immediately, confirming that every component performed exactly as designed.
Once removed, the suit tells its own story, revealing where stress, heat, and motion left their marks.
Every scuff and fiber shift becomes data, helping engineers refine materials for the next generation of missions.
Each component is separated and reviewed, revealing how real-world conditions shaped performance in orbit.
Lessons from every mission feed directly back into design, turning experience into smarter engineering decisions.
Each revision builds on past performance, gradually improving comfort, durability, and efficiency with every new prototype.
New fabrics are pushed to their limits, searching for lighter, stronger solutions that can handle future missions. Engineers now explore new ways to increase flexibility, reducing effort while expanding what future crews can accomplish.
Smaller, smarter systems are being developed, aiming to deliver longer endurance with less weight and lower energy demand.
Digital simulations now predict performance before hardware is built, helping teams identify problems long before testing begins.
Designing for reuse reduces cost and waste, ensuring protection systems can evolve without starting from scratch each time. Future missions demand protection that can adapt to new surfaces and conditions, extending performance beyond low Earth orbit.
Long-term studies reveal how the human body responds over hours and days, shaping designs that protect health as well as survival. At this stage, separate innovations merge into one system, revealing how future protection will function as a complete, balanced whole.
Before it can support future exploration, the complete system must prove it works flawlessly as one, under real operating conditions.
What began as protection has become a pathway, enabling humans to move farther from Earth than ever before. In the end, every layer reflects a balance between human vulnerability and careful engineering.
Each generation builds quietly on the last, refining protection through lessons learned, testing, and constant improvement.
Even as one design is completed, work continues, preparing the next generation of protection for missions still ahead. Building these systems is never a single event, but a continuous process that balances precision, timing, and constant quality control.
Much of this work depends on experience passed hand to hand, preserving skills that technology alone cannot replace.
Automation increases consistency, but critical steps still rely on human judgment, where experience guides decisions machines cannot make. As production scales up, consistency becomes critical, ensuring every suit meets the same uncompromising standards. Before deployment, each suit is secured and protected, preserving months of engineering until it is called into service. Behind every mission is a global network, coordinating support and readiness long before the suit is ever worn. Even between missions, these systems are never truly idle, quietly monitored to ensure readiness is never lost. As missions evolve, new risks emerge, forcing protection systems to adapt before those threats are ever encountered. Safety advances rarely arrive all at once, but through careful improvements that quietly reduce risk over time.
Longer missions demand systems that can be serviced, adjusted, and trusted over months rather than days. Maintenance often happens in tight spaces, where access is limited and precision becomes as important as the repair itself. When systems fail unexpectedly, emergency design features determine whether a situation remains survivable.
Redundant systems ensure that when one pathway fails, another takes over instantly, preserving life without hesitation.
Before approval is renewed, every failure scenario is reviewed again, ensuring no risk has been overlooked. Trust is built through repetition, as systems prove again and again that they respond the same way under the same demands. At this point, readiness is no longer assumed, It is confirmed through data, repetition, and proven performance.
With testing complete, responsibility shifts, placing proven systems into the hands of those who will rely on them in flight.
Regular training keeps procedures familiar, ensuring every action remains calm and automatic when it matters most. Now stored and monitored, each suit waits quietly, prepared to transition from engineering achievement to human survival. Even at rest, conditions are carefully controlled, preserving integrity until the next call to action.
When missions change quickly, deployment systems ensure protection can move just as fast. Before transport begins, containers are tested against impact and vibration, protecting sensitive systems in motion.
Upon arrival, responsibility shifts again, bringing carefully protected systems back into active mission preparation.
Systems come back online, restoring airflow and monitoring as the suit returns from storage to active readiness. Final calibration aligns every sensor and valve, ensuring nothing drift before countdown begins. Rehearsal turns procedure into instinct, so every motion feels familiar when it finally matters.
Medical teams confirm the body is ready, completing the final human checkpoint before launch.
On launch day, preparation becomes personal, as proven systems are worn by the people who trust them most. Each step toward the vehicle carries years of testing, now condensed into a single moment of commitment. Final connections bring external support online, holding steady until the spacecraft takes over completely.
As the countdown proceeds, the suit quietly regulates life, maintaining stable conditions through every final check.
During ascent, the suit manages pressure and circulation, helping the body tolerate powerful forces pushing it back into the seat. Once orbit is achieved, forces ease, and the suit transitions smoothly from launch protection to sustained life support. In orbit, attention turns to operations, with the suit continuing its quiet role in maintaining balance and comfort.
Routine tasks still demand protection, as the suit manages airflow and temperature while work continues in weightlessness.
Over extended periods, the suit must remain comfortable, supporting circulation and temperature while fatigue gradually builds. Regular health checks confirm that every system continues to perform, long after launch is behind them. As re-entry approaches, the suit shifts roles again, preparing to manage heat, pressure, and acceleration.
During re-entry, thermal protection and pressure control work together, shielding the body as friction heats the surrounding air.
As gravity returns, the suit helps distribute forces, supporting circulation while the vehicle slows toward Earth.
After touchdown, the suit maintains stability, supporting recovery as systems return to normal conditions. Back on Earth, the suit continues supporting recovery, bridging the gap between extreme flight and normal gravity.
Medical teams measure how the body adapts back to gravity, completing the human side of the mission.
After every mission, the suit is carefully cleaned and restored, preparing it for inspection and future use.
Technicians compare pre-flight data with post-mission results, confirming how every system performed under real conditions. Key components are refreshed and replaced, extending service life while preserving the integrity of the overall system. Every mission completes a learning loop, turning experience back into knowledge for future designs.
Work immediately turns toward what comes next, applying proven lessons to designs still taking shape.
With every improvement, protection becomes possibility, opening pathways to places humans have yet to reach.
What starts as engineering gradually becomes exploration, turning careful design into human reach.
Between missions, there is a quiet pause, where preparation meets possibility.
As one mission ends, another quietly begins, continuing a cycle driven by precision and purpose.
Each generation leaves behind knowledge, shaping protection systems that carry experience forward.
Attention now turns to distant destinations, guided by systems designed to protect life far beyond familiar orbits.
Behind every system are people, bringing skill, care, and responsibility to every stage of the process.
Trust is built slowly, through countless tests, careful decisions, and lessons carried forward. From design to deployment, responsibility is shared, connecting many teams through one common purpose. Each mission closes a chapter, feeding experience back into systems designed for what comes next.
Every improvement points forward, shaping protection for journeys that extend far beyond today's horizons.
In the end, it is careful engineering that quietly allows humans to exist where they otherwise could not.